This is another electromagnetism question, which you might get something similar related to it in your probably final year of high school if you're doing something like IB or A levels, or you might even see something similar in your first year of your university degree if you're doing physics or some kind of engineering. And if you'd like to see anything similar to this on the channel, let me know in the comments. So, for this particular question, we're dealing with a rectangular wire loop, so just, a rectangle made of wire. And we call this rectangle ABCD. We know the length and the breadth. We're not giving any numbers, we just have the symbols. And we know that the wire has a resistance of lambda per unit length, right? So I think this might be a typo here because it looks like the resistance is lambda L per unit length, but it's lambda per unit length. Unit length. And the loop is being pulled out from the magnetic field at a uniform speed v, so this is constant, which is important, as you'll see. And then we're asked to find the potential difference between two pairs of points. So we have to find the potential difference between points B and C, and also the potential difference between A and D in this way. So let's see what we know and how we can actually find that. So I would start by looking at what happens inside the magnetic field. So I would look on the left-hand side of that vertical dotted line. So let's say if we look at this wire here, this section that we call AD. So we know this is moving with a velocity of v, like this. So all the electrons are moving with a velocity of v to the right. And what happens is that the magnetic field is pointing into the page or into the screen. So as a result of that, we can find the Lorentz force acting on the positive charges as well as on the electrons. So the formula for the Lorentz force is Q and then V cross product with B, right? So if you have a vector v going this way and a vector b going this way, so I'm kind of like rotating the perspective. V and b is this way, then you can use either the right hand rule or the corkscrew rule, which I prefer, to find out the direction of the force. And in this case, we would have a force pointing into the screen from this perspective, and it would point this way from this perspective. So this is FL. But remember, this is the force acting on the positive charges. On the negative charges, on the electrons, it's going to act in the opposite direction, right? And it's actually the electrons that are the physical particles that are on the conductor. There isn't such a thing as positive charges per se. So we're going to use this to say that, okay, there will be positive charges here, or rather there's going to be a lack of electrons here, and there will be electrons instead on this end, like this. So this will create a potential difference, and because the conductor doesn't just end at points A and D, it's a continuous loop. This will generate a current which will have the conventional direction in this way. So you'll have a current that will travel like this and like this. And that's what happens from a qualitative point of view. So the next thing to do at this point is to figure out what is the value of the current, and based on that we can find out what the two potential differences are. Now, because we're in a magnetic field and the magnetic flux is changing, so even if your magnetic field strength is constant, which it is, then your magnetic flux can change still. because here's what we have. We have that the magnetic flux is equal to the magnetic field multiplied by the area. So normally it's a dot product, but I'm going to ignore this for now. And I'm going to ignore it because they're perpendicular to each other. So we have B, which is the magnetic field, multiplied by the area. Now, this is not the area of the full rectangle, but it's the area which is inside that magnetic field. So that's going to be equal to B. And then this area is what I'm looking at. So that area is lowercase b multiplied by this. Okay, so that distance, I'm just going to call it x. And that x is changing. So that x with respect to time is equal to minus v. So it's negative because the distance x gets smaller, and it gets smaller at a rate of v, where v is the constant velocity. So it gets smaller at a constant rate, which means that the flux, which we wrote it as b multiplied by bx, we can find the rate of change of flux, which is d over dt of b times x, which is b times lowercase b times v. And that's the magnitude of the EMF, basically, right? So what we can then turn this into, we can ignore the magnetic field from now on. So we know that there are positive charges here and negative charges here. So I'm gonna write that I'm gonna draw this as follows. So this rectangle will become a circuit, and each side will have a certain amount of resistance. So this side is going to have a resistance, this side is going to have a resistance. Even this side will have a resistance, which I have to draw as well, and then this side will have a resistance too. And the points were A, B, and then C, and then D. Okay, and then the current will flow obviously in this way. Now we know what the resistances are. We know the resistance per unit length of each of the whole wire. So this one would have a resistance lambda L, because that's the length of side AB. This is lambda B. This is lambda L again, and this is again lambda B. So the current is equal to the EMF divided by the total resistance, which is, the resistances are in series, so we can just add everything up, and we get 2 lambda times B plus L. So that's the current. Now, the question is asking us, the first thing that the question wants us to find is the potential difference between points B and C. So we have to do VB minus VC. So we can tell that the potential at B is greater than the potential at C, because that's how the charges are flowing. So that's going to equal the current times lambda B, which is the EMF over 2 lambda times B plus L multiplied by lambda B, and then we cancel out the lambdas, and we get epsilon B over 2B plus L. And that's the potential difference between B and C. Now, another way to do it, if you want, is to imagine that you place an ideal voltmeter here, right? And then you can do Kirchhoff's law. You can apply Kirchhoff's law to calculate the potential between B and C. And that would give you pretty much the same thing. So if you do it this way, if you use the second law of Kirchhoff, you have that there's no EMF, right? So that would be 0. And then you would have, so on this branch, you would have I as the current multiplied with the resistance. So it's I multiplied by lambda B. And then on the other side, you have that reading of the voltmeter, which is U. So if you rearrange this, you get U is equal to I times lambda B, which will be the same as this. And that's the first question. The other question is trying to figure out what the potential difference is between A and D. So let's do the same thing. I'm gonna put a voltmeter like this. That's my voltmeter. And then I'm actually going to take my the direction of the loop in this way, from kind of like from A to D on the above uh, segment of the circuit. So what we will have in this case is the following. So we do have an EMF, which is going to be minus epsilon, because we're following the circuit, from plus to minus, so there would be minus epsilon. And then we would have, remember there's a current here, like this. So we would have minus I times lambda B, and then plus the reading of the voltmeter, which is U. And that's a potential difference we're looking for. So U will be equal to minus epsilon plus I lambda B. So the potential difference will be minus epsilon, which is B times V, plus, and then we have the current, which is epsilon over, or I should say probably, yeah, let's leave it as epsilon for now. And then 2 lambda B plus L times lambda times B, and then we can cancel out the lambdas. So U will be equal to minus the EMF plus, and then this EMF will be the same as before, squared, because there's another B here, divided by 2B plus L. And you can change the denominator of this. You can create a common denominator and solve it in this way, but I'll just leave it in this form. The only thing to keep in mind is that this epsilon should also be replaced with the value of EMF that we got, which is B times B times V, like this. And once you do that, you'll have an expression for the potential difference between A and D, and then between B and C. And that's the end of the question.